So we welcome our speaker, Dr. Samarth Brahmbhatt. I also welcome faculty colleagues and all participants. I request Samarth to start with the presentation.
Yes, thank you, sir, and welcome everybody. And yeah, so today we are going to start the technical part of this lecture series. And I'm going to start with some mathematics and trigonometry about how images are formed and how, at least in computer vision and related fields, we think about 3D world and 2D image and the connection between them. And so, yeah, today it's going to be some formulas and matrix multiplications and things like that. So I'm going to share my screen and write on this iPad. And actually, just like last time, I will really appreciate if anytime you think you don't understand something, you stop me and ask a question. At the same time, if you think this is too slow or too boring, or if something is like a lot of these things are you already know them, then also let me know so that I can skip and go ahead, because I have a list of things to cover today. So yeah, let's start. So I want to start by talking about points and lines in 2D and 3D. So the first concept is what is called homogeneous coordinates. And this is both for points as well as lines. Let's just start with the equation of a point and a line. So you know that a line is something, you can say, a collection of numbers a, b, and c, such that you have ax plus by plus c equals 0. So this is in 2D, right? So then this is a line and the point is xy over here. Now the thing is, if you can represent this as a kind of a matrix multiplication by saying that my point x is actually x, y, and 1, and my line L is a, b, and c. And you can write this same equation as L transpose x equals 0. Yeah, so just, I know there are two x's here, but don't confuse them. I will try to write them separately. This small x over here is just one number, and this kind of other x is a vector of 3 numbers. So yeah, so here we wrote this equation like this, but note that if our line had some kind of a scalar multiplied here, like k, so actually so then the equation would be kax plus kby plus kc equals to 0, which is also true because you're just multiplying this entire equation by a constant. So that means that somehow this line L and line k times L, they're somehow equivalent. So that's an interesting thing to note. And similarly, you can think about it from the point perspective. So if you have a point kx, which would be k times x, k times y, and k, then the same equation would hold true, right? Because you're again multiplying this equation by k. So that means our line has this equivalence relationship, and our point also has this equivalence relationship. So this is what we mean by homogeneous coordinates, that if we represent a 2D point by adding 1 at the end of it, then we get a representation in which x is somehow equivalent to kx. So multiplying multiplying all the 3 elements of that vector by some scalar is doesn't change the actual underlying point. And the similar phenomenon is observed with the line. And of course, in both of these equations, we want k should not be equal to 0. So this is the whole concept of homogeneous coordinates, and actually it has some deep mathematical significance, but right now we are not going to go into that. For computer vision, or at least right now, we can just treat it as a very convenient representation of points and lines. So because it gives some properties to points and lines which will be useful. So let's look at some of those properties, right? So we have also note this symbol. So the symbol basically here says that this kind of wavy symbol is used to indicate homogeneous or equivalence in homogeneous coordinates. So in homogeneous coordinates, we can think about the relationship between points and lines. So we can say, for example, the line passing through 2 different points. Let's say you have 2 homogeneous points x1 and x2. Then the line passing through these points is actually the cross product of x1 and x2. Sorry, there are a lot of x's here, but so this here is actually the cross product. And Pujara sir, this whole whiteboard system is working, right? You can see the writing and everything.
Yes, Samarth.
Okay, good. So if you look at the cross product, let's just say that this cross product right now is just some other vector called L. So if we know that from the properties of cross product, we know that this vector will be perpendicular to both x1 and x2. So that means L transpose x1, L transpose x2, both of them are 0, because when 2 vectors are perpendicular and you do their dot product, then that becomes 0, right? And this is exactly the condition for the representation of a line that passes through 2 points x1 and x2, right? So that means this quantity that we get by doing cross product of these 2 homogeneous points, this quantity is actually equivalent to the line that passes through these 2 points. And similarly, if we have 2 lines, then the intersection of line L1 and L2 is another vector. And similarly, this vector is perpendicular to both L1 and L2. So this is some nice property that if you represent the point and line in homogeneous coordinates, then you do the cross product of 2 points, you get the line. You do the cross product of 2 lines, you get the intersecting point. Now, another advantage of representing things in these homogeneous coordinates is when you want to transform points. So let's say you want, so we can look at transformations. First, we will look at all these transformations in 2D, because our lines and points, everything is in 2D right now. Even though we added a third dimension and we put a 1 over there, but actually the point is in 2D and the line is also in 2D. So maybe you know that a point is actually with respect to a coordinate system. So we have, let's say, our coordinate system, x-axis, y-axis, and we have our point here, which is x comma y. The simplest one is that you want to translate it, right? Let's say you want to translate it, and you, let's say this is point x and this is point x dash, and you want to translate it such that it becomes x plus tx, y plus ty. So then you can say in homogeneous coordinates you have you know, x dash y dash 1 equals x y 1, and you have here dx dy. So actually, since all of these are homogeneous coordinates, let us do one thing. Let us multiply yeah, so let us multiply everything by so this is actually not going to work. So here, let me the simple addition will not work. But what I actually wanted to show is that if we have a matrix multiplication 1 0 tx 0 1 ty 0 0 1, right? So then this is actually exactly equal. Actually, in homogeneous coordinates, it's both equal, and you could also write this sign here. But just in this special case, the equality also holds. So that was translation. Now, if we again want to, let's say we want to rotate the point. So we have xy again. So there is this vector from the origin to that point. We want to rotate it by yeah, we want to rotate it by some theta degrees of rotation. So we kind of want to have here another right. So then what you can do is again you write xy1 yeah. So let me actually do something separate. You want to you have your point here, which is xy. And let's say this distance is actually just 1 here right now. So if you have another coordinate system like this, another x-axis and y-axis, and this angle here is theta. So in this dashed coordinate system, this point is actually just 1, 0, 1. But now if you want to represent that point, this same point, in this new coordinate system, then that becomes, here you have cos theta, here you have sin theta, right? So the rotation matrix, which is, I'm just going to write C and S. Right, so you will get cos theta, sin theta, and 1. So what this means here is that you have effectively kind of rotated this point. So both of them are equivalent. You either rotate the point or you rotate its reference system. So here you can understand it in the sense that you had this point which was in this dashed reference system, and now you kind of rotated this whole thing like this. Sorry, there's this boundary here. You rotated this whole thing like this, and you came to this new coordinate system in which the representation is this. So again, this transformation can be represented by a 3 by 3 matrix. And similarly, now you can also have another thing where you have some general point xy1, you have some rotation and also some translation. Yeah. So you had some coordinate system like this. You not only rotated it, but you also translated it. So this is your old coordinate system. This is your new coordinate system. Now there was some underlying point x here, which was x, y in this old coordinate system. But the same point, so like you can have this vector going that way. But the same point in this new coordinate system will be this x dash y dash point, where this is the translation that you did here. So this is tx ty, and first you rotated it. So like you rotated the, like if you just write, this is your theta rotation angle like this. So first you rotate this coordinate system like this, and then you translate it, and both of them are represented by this same 3 by 3 matrix. Now similarly, like this, you can also have another So this is basically called homogeneous transformation matrix. Similarly, you can have a scaling factor where actually maybe I shouldn't write S because it gets repetitive. Okay. Right, so what you're going to do, let me just write down here, X dash is actually, you're first going to scale this. So this will be and then you translate, right? Is that right? Actually, this should be minus here. Yeah. So the order of operations is something like this. First, you took this point xy, you rotated the coordinate system, then you scaled it, and then you translated it. So this thing is called similarity transformation. I guess the name doesn't matter too much right now. But I just want to say that increasingly we can have more and more elements in this matrix, and it becomes more and more complicated, right? So right now we have, if we had just rotation, then we just had this theta parameter. There was one parameter. Now then we have three parameters, theta, tx, ty, and then we added a scaling parameter k. Okay, and then similarly we can have what is called affine, where this part does not need to have this cos theta sin theta form. It can just be any numbers. So that means you have any numbers in this whole matrix, so that has 6 parameters. And finally you can have any numbers in the whole matrix, but remember that in this homogeneous coordinate system, any scalar multiplier over here can be ignored or can be cancelled out. So then that is equivalent to saying that one element of the bottom right element of this matrix always remains 1. So that means you have 8 parameters, and that is called projective transform. Okay, so there was another advantage of representing everything in homogeneous coordinates, that you can do all these transformations very easily. Now we can do the same.
Meanwhile, shall we ask students if they have any question?
Yeah, definitely.
Students, if you have any question, for example, don't you think you should ask a question why this transformation is required, or how this is relevant in case of image processing or computer vision?
Yeah, I mean, I think that is a good question, and sort of this is the whole background that is needed for basically converting the 3D points. You know, the whole world is made of 3D points, and when you when you have a camera that is moving around in the world that is made of 3D points, then you need to transform all those 3D points by translating and rotating them into the coordinate system of the camera, right? And then you can do various geometry things to get the 2D image from it. And I'm actually going to show an example of it, I think towards the end of this lecture. So this is, I know this is sort of very abstract basics, but this will be useful. I think just in 15 minutes you will realize how this is going to be useful. So when we move to 3D, when we move to 3D, I just want to show you one example from 2D that we had before, right? So we had this pair of coordinate systems, right? And we said that the transformation matrix for that was going to be cos theta minus sine theta, cos theta, and then yeah. So actually look at the columns of this matrix. If what I mean by that is if you look at unit vectors in, let me change the here. If you look at unit vectors in this coordinate system, so this is my unit vector along the x direction, this one over here. If you look at the unit vector here in this new coordinate system, then actually that is, this one is cos theta sine theta. This one here is minus sine theta cos theta in sort of this new white coordinate system. And those are actually the columns of this matrix here, right? So if you want to create a rotation matrix connecting one coordinate system to another coordinate system, basically what you do is you take the unit vectors in the old coordinate system, see what those unit vectors would look like in your new coordinate system, and write them as columns of your 3x3 matrix. So then when we move from 2D to 3D, the same concepts are going to apply. Now I'm not going to repeat everything, but I'll just kind of sort of draw one example. So let's say you have, this one coordinate system, x, y, z, and your sort of other coordinate system, x, y, z. So as we saw, there is some kind of rotation between these two, and there is this translation between these two. So now I'm going to talk about how we can represent this transformation from this coordinate system to this other coordinate system. And this is kind of very important concept in computer vision, because if you think about it, every object, you can think about every object in the world that has its own coordinate system. For example, this phone, you can think of coordinate system where the plane of the phone is x and y axis and my z axis is coming out, right? So now if I want to know how far my phone is from the camera, so you can imagine my eye is the camera. So my eye will have its own coordinate system, right? It will have, let's say, z axis coming out, x axis towards my right, y axis going down. And as the phone moves in the 3D world, if I can represent that with this rotation and translation matrix, then that will be very useful mathematically for me, right? So that is how basically, as we saw before, we can make this matrix. What we are going to do is we are going to take the, as we said, unit vectors of, well, first of all, this translation, this translation in 3D is, we just put it directly here. So tx, ty, tz, and 1. So now this is a
Samarth,
4 by
I don't
4.
know why. Perhaps I'm not able to see your writing on the board. Is it so with everyone?
No, sir. I think it is visible in the board. I think other students.
Whatever he has written just now. Okay,
Sir,
fine. If
he is
it is
written the
visible,
matrix.
yeah, fine. Go ahead.
Yeah. Okay. So now, since we are in 3D, when we were in 2D, all our matrices were 3 by 3. Now, where we are in 3D, all our matrices are 4 by 4, because when we write points here, we will say x, y, z, 1. This is the homogeneous representation in 3D. And now this rotation matrix, it's in 3D, it's not so simple. In 2D, you can just write this cos theta, sin theta thing. But in 3D, you have to actually you have to make these rotation matrices for all the 3 axes differently, right? So let's say I will just write it for the x-axis. So for the x-axis, it will be the rotation matrix. So this is what goes here. This is 3 by 3 block of the matrix. So remember how I'm not going to derive it. You can actually derive it at home if you want to. Rotation around x-axis by angle theta will be so one way to remember it is when you rotate around the x-axis, the y and z coordinates of the points change. The x coordinate actually does not change, right? So that means you have 1 0 0 here, 1 0 0 here, and then you have cos theta minus sin theta, cos theta. Similarly, when you want to rotate around y-axis by theta, it will be 1 here, 0 here, cos theta minus sin theta, cos theta. And similarly for z. And then if you are rotating around all 3 x, y, and z axes, you have to somehow combine all these 3 matrices and multiply them together, and the final result will also be a 3 by 3 matrix. And that 3 by 3 matrix you put over here. Are you still able to see? Someone, can you confirm whether you can still see? Okay, not able
No.
to see. I don't know what happened. Okay, I think it should be back now.
Yes, Samarth. Now it is visible.
Okay. Nice. So yeah, as I was saying, you have to multiply these 3 matrices, and I will tell you how to multiply in just a second. but the result will be 3 by 3 matrix, and that will give us our result here. So that will be another XYZ 1. So remember, this will always be 1 because you have 0, 0, 0 and 1 over here. So if you actually do the multiplication, it remains the same. Now I want to introduce some conventions like how to name various matrices, which will be very useful to all of us. So what this is doing is actually it is taking a point, like let's say this is the point, point P, which was X, Y, Z. This is the actual point, and we were representing it in this old coordinate system. Let's say this coordinate system is A, and now this new coordinate system is B. So what I'm saying is, whenever you want to write, whenever every point is with respect to some coordinate system, so always we should write the reference coordinate system here like this in the superscript. So it's like in the, so that we know it's in the A coordinate system, and similarly this is in the B coordinate system. And if we want to if we want to write this in a simpler form, you know, like in vectors and matrices, then we can say this whole point is XA. So here this X is capital X, right? It's not, here this X is just one number, but now this X is a vector. So don't confuse the two. And this is XB. And we will name these kind of rotation and translation matrices, we will call them T, but we will have B here and A here, right? So that makes it very easy. So you can have, the equation becomes, the point in B coordinate system is this matrix times the same point in A coordinate system. And this is a very useful formula because you can also remember it like this. It goes from left to right. So you start with a point in the A coordinate system. This A and A cancel out, and you're left with B. So now from the multiplication by this matrix, so now you get the point in the B coordinate system. And remember that this whole thing was possible because we added 1 over here, right? So that is also another advantage of using these homogeneous coordinates. And finally, I also want to mention that, let's say after this second coordinate system, we had a third one, right? So X, Y, Z, and this was called C. And then we also know the transformation from here to here. So if we want, if we know from here to here, and we know from here to here, we can directly go from here to here by somehow combining these two matrices. And you can actually derive it yourself, but I'm just going to write it over here. So again, you start in the A coordinate system, you go from A to B, then you go from B to C, and finally you have your point in the C coordinate system, right? So this is called chaining, and you can chain multiple transformations by multiplying those matrices. So these two matrices, you know, they are both 4 by 4. So the result will also be a 4 by 4 matrix, which we will call directly C to A. So now we can use directly this matrix to go from A coordinate system to C coordinate system. Okay, great. So this was some basics about 3D coordinate systems and things like that. So there is some chat about screen is not being updated, but hopefully it is okay.
No, it is updated. So Hanil, please check your side.
Okay, fine. So let's see. So yes, we can combine multiple transformations. And I just want to mention, when I said, how to combine these rotations, you can actually think of this rotation matrix. If you add, this is a 3 by 3 matrix, but if you add 0, 0, 0, 1, and then 0, 0, 0, you can actually make a 4 by 4 matrix like this, right? So this just means that it is a pure rotation because the translation is all zeros. So actually, if you want to get the combined rotation matrix R, Z, Y, X of theta 1, theta 2, theta 3, then basically you first do Rx by theta 1, Ry by theta 2, Rz by theta 3, and you will get the final matrix, right? And then from the final matrix, you can extract the 3 by 3 part and put it there. Because since all of them have 0, 0, 0 over here, no matter how many pure rotation matrices you multiply, you will end up with the same pure rotation matrix. Okay. Let's see. Now finally we are coming to our computer vision part, because all of this was just geometry. So this is called the pinhole camera model. So I just want to ask Pujara sir, or whoever is managing this meeting, is it fine if we do 1.5 hours instead of just 1 hour?
Maybe you can continue at least today for 1 hour and 15 minutes. So next time onwards, we'll keep it 1 hour 15 minutes.
Okay, sounds good. So, So, I think this is very simple trigonometry. So let me just start with the 2D case. So let's say you just have this kind of plane over here, and then you have some object. You have some object, and like there are various rays of light going out from this object in all directions. And now here you have, like when we were children, we used to make this small camera which is just a cardboard with a very small hole in it. So imagine there is sort of like a cardboard here with just one hole, and out of all the rays, one ray will go through that hole and kind of go like this. So now on the other side of this pinhole, if we put a screen, like a paper or something, a white screen, then we get the inverted image of that object, right? And this is, I think you learned this in optics, and also if you want to analyze this inverted image, you can think of this also as like a virtual image on the other side at the same distance from the pinhole. So let me just draw that figure again for neatness. So now we have our pinhole here, this ray, and we are forming an image of this object here. So that means actually our screen was behind here like this, but we are virtually thinking about a screen in front of it. So this is our camera coordinate system. Let's call it C. The center of the camera is here. This is the real 3D object, but we are looking at it from the front, so it's like a 2D view. So the distance here between the camera and the object is z, and the height of this object is x. Now, if we call this the focal length of our camera, which is the distance at which the image is formed, then we know we have this height over here. And we know that this bigger triangle and the smaller triangle are similar triangles, right? So we can write u divided by f is equal to x divided by z. So this is one of the most important equations, because what this does is it tells us how the image is going to be formed from a 3D object. So let's look at this whole thing in proper 3D. So typically the coordinate system of a camera is kind of weird. So typically the convention is that you have x going here, y going down, and then z axis pointing forwards like that. And now the image is going to be formed somewhere like somewhere here, right? So that means if you have a point P at x, y, and z, then you can draw a ray. So let's draw this ray going from the center of the camera. Let's say it intersects this plane over here, and it goes all the way to this point P. So the main part of this lecture I want to talk to you about today is when you have a point in 3D like this, and then the ray of light from each point like that, all over in the whole world, they're all going to come in and they're all going to intersect at various locations inside on this image, like this. And their image points are going to be on this plane. Now this plane is just a 2D plane. So now it only has x, y, or what we called UV, right? You can say UV. So these are 2D coordinates. Now this is 3D coordinates. So you convert it from 2D to 3D. And what is that conversion? So here, like for example, this is the U axis, this is the V axis. So U is my focal length, X, and then V is my focal length times Y divided by Z. So I hope this is, you can kind of extrapolate from this 2D diagram that when you actually do this thing in 3D, this is what is going to happen, right? Because like you will basically have actually a 3D triangle like that, because like you have this 3D triangle here, and then you have this like smaller 2D triangle here. You have similar triangles, but they are going to be in 3D. So these are what is called projection equations. They convert from 3D to 2D. How can we write these using homogeneous coordinates? So what is going to happen is I will write the 3D point just in normal 3D coordinates, and then I will write this matrix right, and I will say my small x is homogeneous equivalent to this. This is the most important part over here, because if you actually do this matrix multiplication, what you will get is fx, fy, and z. But remember, if we consider this as homogeneous, if we consider this as the homogeneous representation of a 2D point, right? So then the underlying, so then we can take out this z, right? So we can say this is, remember in homogeneous coordinates, we can take out the scalar. So this is equivalent to z times this. And this is, these things are exactly what we had over here. So what this becomes is our u, v, and 1 is homogeneous equivalent to x, y, and z, right? Because when you actually multiply, you will get z here, but since it is homogeneous, you can divide the whole vector by any scalar. So if you divide the whole vector by z, then we get actually our fx by z, fy by z, and 1, which is actually what we called our uv point, which is our 2D point. Okay, so I will pause here and ask if somebody has questions about all this mathematics, because this is an important equation.
Yes, students, this is a wonderful opportunity. You should ask questions and interact. If you interact, if you ask queries, doubts, then only you also will enjoy and the presenter will also enjoy. See, initially you may feel that why this mathematics or this mathematics is quite boring, but ultimately this is the foundation of computer vision or image processing or maybe signal processing. So I am also attending this lecture not as a teacher but as a student, as a participant. So at least today I have learned a few important mathematical terms, formulations. I think that is very, very important for anyone who is planning to make his or her career in the field of computer vision. So if you have not understood, ask. Plus, I will suggest that after this lecture, maybe Dr. Samarth can suggest you some reading material you should read and make yourself ready for the third lecture. See, if you will not understand the fundamentals, perhaps you will not enjoy the future sessions. So it is my humble suggestion to all of you, please ask question, make it interactive, interesting. Anyone?
I think it's fine because people might have questions after going through the video again, or maybe this is ultimately this is just maths matrix multiplication. So I think people can also probably easily understand at least the mathematics of it. Maybe they yeah, I think okay, cool. So I will continue, but just remember that this whole video is going to be uploaded on YouTube, so you can watch it again. And I will also convert this whole notes to PDF and send it to everybody. So I will continue. Hopefully this is like a very basic equation about how to convert our 3D point XYZ to a 2D point UV. Okay. Now this UV is 2D, and so our image plane is also 2D. So let's look at how the images are actually going to be stored in our computer. So in our computer, let's say you must have heard about arrays and things like that. So actually in our computer, the image is stored as a 2D array, sort of like this, right? The image is rectangular, and each of these things is called a pixel. Pixel over here. So typically, if you know in Python, you have in NumPy, you can have this kind of 2D arrays and things like that. So typically the indexing of this array starts from here. So this is 0, 0, and this is 0, 1 up to 0, some kind of width, right? And now this is 1, 0 up to 1, width. And now we have our height, 0 and height, width. So this is how an image is stored inside a computer. So you might also have, for example, store it in NumPy or something like that. So let me redraw that image that I had over there. Right. So we have that, and our image plane, which is, I know it's really hard to draw it correctly in 2D because there is actually a 3D concept. But imagine that this z-axis is going forward and this plane is actually sort of in front of the camera. So the z-axis is going in front of the camera like that. So if we convert this kind of representation, then in our UV axis, we actually want sort of like this, right? So this will be the origin of our 2D coordinate system of UV, and this here will be width and height. So there, as you see, there is sort of a correspondence between U and X and V and Y because they're kind of also going in the same direction. So if there is some point and its X coordinate increases, so like it goes towards the right, then on the image also its point will also go towards the right. Similarly, if it goes down, so its Y coordinate increases, then in the image also its V coordinate will increase, right? So that is fine, and our equations actually reflect that, right? So if my X increases, my U increases, if my Y increases, my V increases. The interesting part is this Z. That means Z is actually the distance from the camera to that 3D point, or like here from the camera to that 3D point. So the higher the Z, the smaller my U and V, right? So that means if my point goes farther away like this, then my then the sort of the image of it will actually go towards the central point. Now remember, this central point is not the same as this 0, 0 point, right? So actually, if you actually imagine the this is the same effect that you see of, you know, when an object goes farther away, then it becomes smaller and smaller, right? So because it is being divided by z. So that means if I take again my image plane, and this is my z-axis. So the point where my z-axis of the camera intersects this plane of the image, that is a special point. We are going to call it CX CY, right? That is because that is where, if a point is exactly on the z-axis, it is going to be projected to this point CX CY. But remember, our 0, 0 is over here, U and V. So now somehow when my, let's say when my x and y are 0, but my z is, you know, z equals to some value k. When my x equals to y equals to 0, then this goes to Cx Cy. But in our equation, we just had this. So if my x equals to 0, my u becomes 0. So therefore, we need to add this number Cx over here. And similarly for v. So this is an offset. And I will let you know, in the next lecture how to actually find these Cx, Cy values. But for right now, for understanding purposes, because of our image, in our image, we defined our coordinate system over here. So there is kind of an offset between that coordinate system and this coordinate system, and that is represented by this Cx, Cy. So we have to add Cx, Cy here. That means if x equals to 0, my u becomes Cx. And when y equals to 0, my v becomes Cy. So our equation is updated like this: f 0 Cx 0 f Cy x y z. So let us actually just do this matrix multiplication. So here this is this thing, but if we want to have actually calculate the equality, let's just call it u dash. So u dash will be fx plus cxz. V dash will be fy plus cyz. And let's say the third element might be w. So w will be equals to z, right? So now from this vector, since both of these are homogeneously equivalent, we can take this w out, right? So we can take this w out and we will get uv1. So u equals to u dash divided by w, v equals v dash divided by w, and our w is actually z. So that's how we get this and then we are just going to divide by w. So 1 equals 1. Okay, so these are the same equations that we actually got by looking at our image right here. So that's why this thing over here. And so the important thing finally I want to mention is this is a very important matrix. This is called the Intrinsic Matrix. And why it is important is because it captures the whole behavior of the camera, right? Because if you know just this matrix, then you can convert any 3D point to its location on the image, right? So, you know, like there this fx, cx, cy, and this distance here is f, right? So you take any 3D point, you know where it is going to be on your image. You have another point here, it will be here. You have another point here, it will be here. So this matrix is really important. And finally, I just want to add that usually different cameras, they have different focal lengths in X and Y direction. So the actual intrinsic matrix, we can call it fx. So previously we just had the same f value on both the x and y axis, but now we are giving it freedom to have different focal lengths along the x axis and y axis. Because actual physical cameras, when you manufacture the cameras, that is the sensor of the cameras is not square, but it's actually rectangular. And I mean, that does not affect the focal length, but the actual lens and things like that, they are different along different directions. So, and this is denoted usually by K. K is your 3x3 intrinsic matrix. And finally, I just want to mention one thing. So now we are going to connect the, you know, those 3D transformations that we had before and this projection equation. So let us say we have some object like a mug. Okay, so we have this mug, it's a 3D mug, it has its own coordinate system, and now we have this point here. So we will call it this is our coordinate system M, right? So M for mug, or actually let's just do coordinate system O for the object. So now we have this point, which, as we said before, we are going to say XO because it's in the object coordinate system. Now a camera is looking at this mug, right? And it's forming this image. Like rays are coming, they are going to like come here. Now this camera has its own coordinate system. Sorry, this is Y and this is Z. And this one we are going to call C. So remember, when we drew this whole image over here, this point, you know, this point over here, this point X, Y, Z, or in fact better is this one. This point was actually with respect to the camera's coordinate system. It was in camera's own coordinate system. But now we are introducing a new coordinate system of the object. So, you know, the mug might be 5 centimeters tall. So this point might just have, you know, like 5 centimeters along the z-axis. But with respect to the camera, it might be at some totally different reference point. So now we want to first go transform this point to the camera's coordinate system. So for that, we need to know the connection between the camera coordinate system and the object coordinate system. And we will talk in later lectures about how to get this connection matrix, but we already know how to represent it, right? It is a 4x4 matrix, TCO. What this TCO does is it will take points in the object coordinate system and convert them to the camera coordinate system, right? We learned about this. So for now, set aside how we are actually going to derive this matrix. But if we know this matrix, then we can transform this same point in the camera's coordinate system, which is this XC. And then we can multiply by that intrinsic matrix. So then we can multiply by that intrinsic matrix and we can get this point U comma V, right? So whatever you want to call it, small x, and this is homogeneous equation over here. So effectively what we did is something like this. We started with a point in the object coordinate system in homogeneous coordinates, which is 4x1 matrix. Then we multiplied it by this transformation matrix, which is 4x4. So the result is going to be 4x1, right? Now, then what we can do is this is actually XC, right? This is also going to be 4x1. But remember, when we derived this equation, this was actually 3x1, and we had actually dropped the 1 here because the 3D point does not need to be in homogeneous coordinates, at least for this projection from 3D to 2D. So similarly, we can do that over here. When we get this point, we can, it will be sort of, you know, X, Y, Z1. So we can actually remove this 1 here. And I'm actually not going to write it as a separate step, but I'm just going to sort of write it like this. And then we multiply by K. Oh, sorry. It's actually now homogeneous. And then we get this point in our image, which is UV1. Okay. So this is how the chain goes.
Samarth, maybe we can stop here for the day.
Yes, sir. Let me. Yes, I think that is fine. Do we have 5 minutes? I just want to introduce the homework.
Yes, yes, sure.
Okay. So yes, sorry, it's taking a long time. But the first homework is actually quite simple. So yeah. As I said last time, we are going to have a Colab notebook. So actually, if you don't understand everything right now, don't worry. I will send a detailed email with what you need to do. But I have written a lot of code. All you need to do is just all you need to do is just write a few lines of code from, because these are the lines. So actually I'm showing you what you need to write, but you just need to write a few lines which implement this projection system. that we talked about. So I just want to run this notebook here. These are like various cells that you run. So it will define some 3D data of a cube, right? And this is your homework part, which I will send you in the email what you need to do in the homework. But then finally, it will take that cube and project it into the image and show it to you. And if you wrote the projection equation correctly, then you can change various parameters of the camera. So remember, in the camera parameters, we had the focal length, Cx, Cy, and then we had the translation of the camera and rotation of the camera. So here you can change everything. Let's say we take the camera farther away. So then the object will become smaller. We bring it nearby, object will become bigger. If we rotate it, the object will also rotate. If we decrease the focal length, then we can see if we decrease the x-axis focal length, we can see it getting thinner in the x-axis. If we increase, then it gets thicker in the x-axis. And similarly, Cx, Cy kind of shifts the object. So ultimately, this is just the same cube, which is at the same position, but it is being viewed through different cameras with all these different parameters. And when you do that, you can see how that camera parameter changes. So actually in this homework, I've written all the code. You don't need to do anything. All you need to do is when I release the homework, I will actually blank out this function. So just be honest and don't read these lines and actually implement the function which takes in 3D points and outputs the projected 2D points. And if you wrote that correctly, then you should be able to change all these sliders and see their effect like that. So yes, I think that is it for today.
Any question from the students?
Please give me feedback if this is too fast or too slow or something you don't understand, something like that. I am going to kind of create an email group so that you can send me questions and I can also send you announcements about how to do the homework and instructions and things like that.
Samarth, it is a very nice lecture, and you have explained this mathematics stuff in very simple way. And I enjoyed this lecture, and I also note down many things in my notes also. And at the end, you have also explained how the 2D, 3D point convert into the 2D, and so the explained with some geometry equations also, and some graphical also. So I think it's very good lecture, and I think most of the students get the benefit from this lecture. So students, if you have any questions, so please ask. It is very important lecture to start the computer vision, right? So
hello, Samarth.
Yeah. Yes.
I have one question that the last part that you have shown in the code and the cube was that, so the cube was of from the one camera perspective or more than one? Because if we take the image of a cube from only one camera, then we cannot see all the four sides of that.
Yes, that is a very good question. because the back half of the cube is not visible, right?
Yeah.
And so this whole field is called rendering. And when you actually consider the cube as a solid, then when you do the rendering, then you will see that the solid surface blocks the rays coming from all the things behind it, and that's why we cannot see the back half of the cube. But here, just to kind of show the concept, I just represented the cube as 8 vertices, and then I plotted all the vertices.
Okay.
So that kind of, the cube is not solid, it's kind of like a virtual cube just made of 8 points, and all the 8 points are being projected.
Okay. Thank you, Samarth.
Yeah, I think that's it. I think I also saw some feedback that students mostly understood these things, so that is great. I will clean up that notebook and release that, and also upload the video to YouTube. So I think that's it for today.
Okay, thank you, Samarth.
Yeah. See you everybody next week.
And Samarth, can you suggest us some reading materials or any textbook for the same topic so that students can also refer before the next lecture, right?
Yes, I will do that. I will do that in the email that I send out. Yeah.
Okay.
Okay, thank you. Friends, now you can take leave. Thank you so much.
Okay. Bye.
Okay, bye-bye.